So today we are going to continue our discussion and to learn Fourier transform and the Fourier analysis of signals. What we are going to cover is the Fourier, the frequency domain and time domain signal properties, and also going to cover the properties of Fourier transform for discrete time signals. So those properties include symmetry properties of Fourier transform and the Fourier transform theorems and the properties. This is similar to what we have done for the Z-transform. When we learn Z-transform, we also list the properties of Z-transform and kind of going through list by list and prove a few of those. So we are going to do the same for the Fourier transform. So for the frequency analysis, we have this Fourier series expansion of Fourier transform. And there are, in general, there are 4 different items. The first is Fourier series expansion for continuous time periodic signals. And why do we have a series expansion here? Because I have a periodic signal. So in one domain, it's periodic. The other domain, discretized. If in one domain, it's periodic, in the other domain, there will be discretized. Just discrete. It's discrete. So if the signal in the frequency domain is discrete, and then we need to use a Fourier series expansion. So the second item is if I have a continuous time aperiodic signal, and then I have a Fourier transform corresponding to aperiodic signal. Aperiodic signal, therefore, in the other domain is continuous. I have to use an integration to calculate. Therefore, it's a Fourier transform. Similarly, if I'm dealing with a periodic signal, but discrete time, a periodic signal, that means it's discretized. So I need to use a Fourier series expansion. It's in the summation. And then here we have discrete time. That therefore, I know somehow implied here, it's also periodic in this part. Periodic on the frequency domain, and we will see that in the formula. And the last item is for discrete time aperiodic signal. So again, aperiodic signal stands for a continuity in the other domain. So I'm using a Fourier transform integration, but it's discrete time, discretized in time. Therefore, it will be periodic in the frequency. It's also periodic. So in these two cases, it should be in frequency. It should be something periodic. So we got something around 0, and we have another copy around Fs, right? Fs stands for sampling frequency. And we have 2Fs, negative Fs, and so on and so forth. It's periodic. Okay, so we said that the continuous time signals have aperiodic spectrum. Discrete time signals have periodic spectrum. Spectrum is just talking about a signal in the frequency domain. And then periodic signals have discrete spectrum. Aperiodic finite energy signal have continuous spectrum. So to see that in pictures, we see that we can put that into 4 different groups. So here, the top left is I'm dealing with continuous time signals here, and the top left picture is in the time domain. It is continuous but periodic. This is periodic. Time domain is periodic, and these are the signals originally developed or explored by Fourier. So it was dealing with those continuous signal, but it's periodic, like a pure sine wave, a sinusoidal function, a pure cosine function. So if you look into the frequency domain, it will be a discretized in frequency. So we're using Fourier series expansion, but because it's continuous in the in the time domain, then I will not show a periodicity in the frequency domain. So it's a spectrum, but it's discretized. What we use for math expression, it is using that. So we have a Fourier series expansion here. This is from the original signal in time domain is decomposed or expanded as a sum of those harmonics, weighted sum of harmonics. If you want to calculate all these weight, C sub case, then we need to use integration because it's continuous. So this is how we calculate from the time domain signal back to the frequency domain weights. And this is what we, starting from the frequency domain weights, all these C sub case, and to recover the time domain signals. Now the bottom left is continuous. It's continuous, but aperiodic signal. So it's continuous aperiodic signal. And then we have a continuous aperiodic signal in the frequency domain. That's the Fourier transform. So you look at, this is in general, that's a signal in time domain, a signal frequency domain. So we have a Fourier transform, that's integration on both sides because they are all continuous, and then integration is from negative infinity to infinity. It's aperiodic. On the right, we have discrete time signals. Now, discrete time signals is something that we will deal with because we are dealing with digital signal processing. So it's the signal is discretized in time, discretized in time. So first, let's look at the bottom right. Bottom right is discretized and aperiodic. So discretized aperiodic with all these signals xn. Therefore, in the frequency domain, will be periodic. So we know we have those copies. One is at 0, another one at 2 pi. As I said, 2 pi is actually corresponding to frequency fs. So, and then we have negative 2 pi, that's negative fs. Now we also have 2 fs, and those continuous different many copies. So the formula we are going to use is here from the time domain to the frequency domain. That's a direct Fourier transform. So the direct Fourier transform is a summation because it's dealing with discretized time. Xn, so we sum all these together. Of course, sum with all these harmonics, e to the power negative j omega n. And the other direction is we have this inverse Fourier transform, which we got the frequency domain signal and times e to the positive j omega n, because it's continuous in frequency. Therefore, we need to use integration. And also because it is periodic with a period with the window of 2 pi, therefore the integration should be integrated over just one periodic window. That's over 2 pi. And then divide by this window size. So we'll divide by 2 pi. And then we got original frequency time domain signal xn. And the last part is the top right. Top right is time domain is discretized. Frequency domain is also discretized. Now, in practice, these are the signals we are dealing with, because once we process these in a computer system or on a digital signal processor, and everything is discretized, you will not be able to store those continuous valued signal. It's always stored in discretized format. So whether in time domain or in frequency domain. Therefore, for the discrete time signal in time domain, I also want it to be discretized in frequency domain. Then it requires me to treat the signal in both domain as a periodic signal. Right, let me say it again. I want to have discretized in both domain. So it translates to the other domain that has to be periodic in the other domain. So I have to make it periodic in time domain and in frequency domain. Therefore, what we have here is I got a window of periodic from 0 to n-1, actually n-1. N it's a repetition of this 0. and the window size is n. Here, the same thing. My window is from 0 to n minus 1 with the window size of n. And that makes a lot of sense because I'm not going to store the entire sequence. I have to have a finite amount of those signals. So this gives me a convenience. I only need to store a window of those, whether it's in time domain or in frequency domain. I only need to store n numbers, right? So indeed, that's how we deal with a Fourier transform in discretized. So we got this xn. Xn, I'm only going to take one window, n summation from 0 to n minus 1. And then, of course, that's the core. We will see later. Its core is e to the power negative j 2 pi kn over capital N, sum over one period, and divide by n. That's the window of n. Then we get this frequency domain signal, which in this case is discretized weight. So it's C sub k. Similarly, if I have C sub k in the frequency domain, we can multiply this core, which is harmonics, e to the power positive j 2 pi kn over capital N. And then we sum this over of one window, which is k from 0 to n minus 1. Now, in this case, I don't have the constant n to divide here. You can either put an n in this forward equation or put 1 over n in the reverse equation. Or sometimes people like to put 1 over n square in this equation, so you can put another 1 over n square in this equation. The reason is that I want to make sure that those two equations look similar. Therefore, it can be implemented using one set of program in my DSP. Okay, so that's how we do with discrete time signal, periodic signal. And therefore, in reality, what we do is we only take signals, within one window from 0 to n minus 1. If I am using discretized in frequency, 0 to n minus 1, everything is discretized. What we implied is that in the time domain, all these beyond this window I'm taking, it should be periodic. It implies that I don't have to. Or putting another way is that if I'm taking those n values of signals and do my Fourier transform, but this is discretized Fourier transform. What I meant is I implied out of my window, these signals should be, the statement is saying that periodicity with period alpha in one domain implies discretization with spacing 1 over alpha in the other domain, and vice versa. So, and let's say one is the periodic is Fs. For instance, I'm substituting this alpha with Fs. So from here to here, this n is really stands for Fs. That's a sampling frequency. Now, what does that give me? The discretization in the other domain, in the time domain, was that's a spacing, right? This the spacing set between every two samples here, discrete samples here. This 1 over alpha, so that's 1 over Fs in my example, which is exactly the sampling period. So indeed, the spacing or the step size in the other domain of discretization, that's 1 over alpha, 1 over Fs, that's the sampling period. The notation for Fourier transform, so we are dealing with discrete time signal, xn, discretized signal. And doing a Fourier transform, we have this summation. So we have xn multiplied by the score, which is e to the power negative j omega n. And then we have summed them together, got a frequency domain signal x omega. The inverse Fourier transform is we take x omega frequency domain signal using f to the power negative 1 that indicates this inverse Fourier transform, which is the reverse or the analysis equation. So we have x omega times the core e to the positive j omega n, the integration over one window, that's 2 pi, So integration from negative pi to pi of this thing, d omega, and divide by the window size 2 pi. We call that a Fourier transform pair, xn and capital X omega. X omega is periodic with period 2 pi, as we see here, and also because the time domain signal is discretized, is xn discretized. If signal is complex, it can be expressed in a rectangular form. So let's look into some detailed signals. If signal is complex, it can be decomposed into those two parts, right? Real part and imaginary part. In general, I can always do that. And then the signal in the frequency domain can also be represented in this rectangular form, real part plus j times imaginary part. In this case, we need to deal with the complex number because I'm going to multiply by this harmonics, which represented by a complex number anyways. Right? It's the exponential e to the power j omega n, e to the power negative j omega n, using the Euler identity. So it's not real cosine and sine function. So therefore, I am dealing with complex number. When a signal satisfies some symmetry properties in the time domain, these properties impose some symmetry conditions on its Fourier transform. So we are using the rectangular form, and everything is in real part, imaginary part. Therefore, the core exponential or the harmonics in my Fourier transform, I also want to express that into those two parts, rectangular form. So using the Euler identity, we have a cosine omega plus j sine omega. Therefore, we can calculate the Fourier transform, we can calculate separately the real part of capital X and the imaginary part of capital X. So it can express in these two equations, where everything here now is a real number. Right? Everything here is real number. This is real, this is real. Xi itself is real. Cosine is real, sine is real, so on and so forth. And the inverse Fourier transform can be also calculated separately for the real part time domain signal and imaginary part of time domain signal. Also, we have those two equations, then everything in it is a real number. Okay. So doing some quick analysis. For a real signal, real signal meaning that my time domain signal, xn, it only has a real part, it does not have imaginary part. So when we plug into the Fourier transform from the previous page, we know this part goes away because there's no imaginary part, it's all zero. Therefore, what we left here is a summation of xn times cosine omega n. Similarly, capital Xi, imaginary part, is equal to a negative sum xn times sine omega n. The second part has canceled out because I don't have imaginary little xi. It follows that the Fourier signal or the frequency domain signal, capital X has a real part that is even symmetric, and the imaginary part is all symmetric. Now, why is that? Well, if you look at that, we got a cosine function, right? Cosine function is even function. Therefore, you sum these all together, you still get an even function. And here, sine is an odd function. So you sum all these together, you still have an odd function. Therefore, we got those two properties. And that gives us this, which is the Hermitian symmetry, or some people call that conjugate symmetry. Hermitian is just meaning that the conjugate of x omega equals to x negative omega. So we have a symmetry, but it's a conjugate symmetry. We call it Hermitian symmetry. The real signals, we got those. The even part, the frequency domain signal is even of the real part, odd of the imaginary part. Similarly, we can discuss about in a polar format. In the polar form, here is the magnitude of my frequency domain signal. It is an even function because absolute value of x negative omega equal to absolute value of x omega. And the the phase of this frequency domain signal is odd. So the angle of x negative omega equal to negative angle of x omega. It's an odd function. We can talk similarly about real and even signals. So it's even better now. This is the signal is real, so this is 0, and the signal itself is also even. So x negative n equal to xn. Therefore, we plug into those equations. We can further to deduct that capital XR, because this is even, so I can put this sum of just one side beyond 0, and from 1 to infinity times 2 with this weighted sum. And then we leave just one term here in the middle, that's x0. This entire thing is even. X imaginary will be 0 because we have the sine function is odd function, and then you have this, all these x is even symmetry. So if we are looking back here very quickly, so we got this part, right? Sine is odd function. Now you give me the x is even function, then it's everything canceled out. So x I is 0. So it has the real value of spectrum, which is even function of the frequency omega. And it goes on. I will just go quickly on this. It goes on if we have a real and odd signal this, and then the frequency domain signal has imaginary value the spectrum. There's no real part, which is odd function of the frequency omega. It's odd function. It's a sum of all these signs. Now, if I have a purely imaginary signal, which means I only got this part, xn is this part, but xr, I don't have real part. We can conclude that the frequency domain signal, the real part is odd. The frequency domain signal, imaginary part is even. If I have a purely imaginary or an odd signal, so I'm adding one more condition here, and then it has a real valued spectrum, which is odd function of frequency omega. So we have a sum, but it's a sum of all these signs. And in the imaginary part of frequency domain signal is 0. Purely imaginary and even signal. So it's purely imaginary and even. The imaginary part is even. Then it has imaginary valued spectrum. We have only this part, that's 0 here, which is even function of the frequency omega. And that is a sum of all these cosines. So these can all be deducted from the basic identity equation or the basic Fourier transform equation. Then we come to this, this nice chat about the properties of symmetry. Summary of symmetry properties of the Fourier transform. In the time domain signal, if it's a real signal, if it's even, and then if it's real and even, we know the frequency domain signal, it comes here. That is also the real part is even, and I don't have the imaginary part, so it's a real signal. If the time domain has only real part, but it's odd, and then it will goes here, if this, and it goes here, the frequency domain signal has only imaginary part, which is odd. Now the time domain signal has 2 parts, so we can follow this map, and you can find out on the other dimension what kind of signal we have. Right. So the previous one is very a broad discussion about symmetry, and as much as we like symmetry, but we don't use that too much. And as long as we understand that it all comes from the Fourier transform definition equation, and we can always come back and to find out if my frequency domain signal has a real part, imaginary part, or either part is real or is even symmetry or odd symmetry. Okay, now we get to some of the Fourier transform properties. And these properties, we are going to use that a lot in calculations, and we're using that a lot in applications. That actually reflects the properties of Z transform. We will see a lot of very similar, and no surprise because Fourier transform is a special case of Z transform. The first one is linearity. If I have a Fourier transform pair, x1 and capital X1, x2 and a capital X2, then this combined signal, linearly combined signal, has a Fourier transform, which is a linear combination of the result, Fourier result of the first signal, combined with the Fourier result of the second signal. It's also combined, weighted alpha 1 and alpha 2. Okay. So what we have here, if you plot this in a block diagram, that means I have x1, go through a Fourier transform, you got capital X1, Fourier transform, x2, I got a capital X2 omega. Now, if I have a combined signal, alpha 1, x1, alpha 2, x2n, which means I have a signal that's coming here, x1n, multiplied by alpha 1, x2n, multiplied by alpha 2. And then you combine them together and go through the Fourier transform, right? And you have the result, let me call this x omega. This is what we have here. If I want to do a Fourier transform, this is the same as if I'm going through the Fourier transform first on each signal, x2, go through this Fourier transform, and then weight it with alpha 1, alpha 2, and add them together. Okay, that will give me the same answer of x omega. So it's linearity. I can break that Fourier transform onto each element of my original combined signal. Okay. Second property is time shifting. Time shifting is if I have a Fourier transform pair, little xn, capital X omega, then if I have a time delay, so the signal is xn minus k, then in the frequency domain, I'll have capital X omega multiplied by e to the power negative j omega. Okay, that's a time shifting. Now, if k is a positive number, then that's a time delay. If k is a negative number, that's a time advance. We are looking at a future signal. So here is what we have for time shifting. Remember what we have in Z transform. Okay, if I'm doing a Z transform, what do we have here? Z transform. That is x z times something, right? Times, let me put in here, times z to the power negative k, right? This is how much we delayed. If let's say x n minus 1 with 1 delay unit, and then do a Z transform, we have here is xz times z to the power negative 1, right? This is what we said. We have a delay unit, so we put a box that's z to the power negative 1. So in general, that's a time shifting property of Z transform. Now, if you look at these two items, that and that, so e to the power negative j omega k equals to this. Therefore, Z is what? Z is e to the power j omega. Yes, that's what we have, right? This is this is in the complex plane. That's a unit circle. That's a unit circle. So we are looking at something with amplitude 1. The mode is 1, and we only have this phase term. So indeed, you know, this is this unit circle. Unit circle. That's how we indicate it in this way. No surprise, because the Fourier transform is a special case of Z transform. Fourier signal is we are examining the signal in Z transform, but we are only going to travel along the unit circle. Okay, so these time shifting properties should be the same like this. Time reversal. If I have a signal pairs, x and a capital X, then x negative n in frequency domain is capital X negative omega. So we can prove that easily using the original Fourier transform equation. Then to look into that from a physical point of view is that if you're counting a signal from future to past, time reversal is as if you are observing, you are measuring the signal from the highest frequency to lowest frequency. Basically, you flipped your spectrum. So it's kind of a time reversal. You will give me a frequency reversal. It's kind of speaking reversal. What I mean is you flipped the high frequency to low frequency to high frequency. Convolution theorem. Convolution theorem is very important because we are dealing with a digital signal system, digital signal processing. We got a system. System itself, we are using mathematically a convolution to deal with that. So we have here, that gives me yn. Okay. Eventually, we need to deal with a digital system that is xn convolved with hn. So I need to know how to deal with convolution. So the convolution theorem said if I have two Fourier transform pairs, then the convolution in the time domain of those two signals becomes a product in the frequency domain of those two frequency signals. Therefore, here what we will have is we just replace the input signal with x1, this impulse response with x2. Therefore, y omega equal to x omega times h omega. Okay, very similar with what we have before. We had before is yz in the z domain equals to xz times hz, right? So here again, that's a product in the other domain, in the frequency domain. Correlation theorem. Correlation theorem is that I have those two signals, x1 and x2. They are corresponding Fourier transform, or the frequency domain signal is capital X1, capital X2. Then the correlation, cross correlation of these two signals, it's going to show me, we call that a spectrum, but it's kind of a cross spectrum. It's not a spectrum of a signal. It's kind of a spectrum S, but it's working on two signals, X1 and X2. And that is capital X1 omega times capital X2 negative omega. So we're simply taking another one of those signals and doing a reversal. Doing reversal in this case, the reversal in kind of flip the frequency negative omega. Now, how to prove that? Well, easily from the previous properties, right? We know a convolution is this convolved with x2n. That is x1 omega, x2 omega. So what is correlation? x1, x2 correlation. Correlation is a convolution. If I'm using L, so I need to using L here, is convolved with the time reversal of the other signal. L is just a lag between those two signals, how you're aligned. It's a time index, you can use N, doesn't matter. So that's the correlation. You can use a convolution, but the other signal is the time reversal. Therefore, indeed, from the previous property, I know I'm going to take here the time reverse signal. So I'm going to use x2 negative omega, which easily prove this correlation theorem. The Wiener-Khinchin theorem. If xn is a real signal, and then we have this autocorrelation of the signal in the frequency domain, that's the spectrum. That's the energy spectrum of the signal. Where does this come from? Well, come from the previous one, where you just change one y to an x. So you have the autocorrelation. The autocorrelation corresponding to the spectrum density. As we said before, this is quite useful in a practical use. in practical cases, we use that a lot. Sometimes it's difficult to measure the signal. Relatively, it will be easy to measure the autocorrelation of a signal. And then we can take the autocorrelation, find its Fourier transform, so we still get the spectrum. In this case, that will give me the energy concentration in the frequency domain. So we got something maybe in the frequency domain like this. That is my S, capital SXX, function of frequency. If I don't care too much about the phase, I only care about, I only care about this. Oh, excuse me, capital X omega. And then maybe that's sufficient for me to look into the power spectrum, the spectrum density, whether it's power spectrum density or energy spectrum density. It depends on whether your time domain signal is periodic or aperiodic. By looking at this density, I can know the energy concentration, whether it's a low frequency signal or it's a high frequency signal. Okay, time shifting. Time shifting is that if I have xn multiplied by harmonics e exponential e to the power j omega 0n, then in the frequency domain, we are having this, that's x omega subtract omega 0. So we have a shift in the frequency domain. Now to prove that, very straightforward, we can use the Fourier transform expression. We can easily prove that. Now what is this? What is this? This is if you know something about communications, we know this is a modulation or upconversion. You modulate it onto a carrier frequency. Basically, you have a signal xn multiplied by e to the j omega 0, which if in communication system, we call it a carrier frequency, omega c, carrier frequency. It can be a high frequency of 10 gigahertz, of 10 megahertz. And then once you multiply this, and then what you did on the signal is that you shift this to a higher frequency. So let's say if in the frequency domain, originally I got a signal here. Oops. Oh, that's okay. This is my x omega. Now you multiply by this term, you multiply by this. This is it's a pure sine wave. It's a sinusoidal function, right? It's just cosine sine with only one frequency on this omega c. What you have effectively is that you are going to modulate the signal, move that from 0 to frequency omega c. So move it here. Frequency shifting. Okay, that is x omega. Actually, we are only looking at the absolute value, the move. So that is the frequency shifting. That is in communication, that's a modulation. You modulate onto the frequency, onto a carrier frequency. Modulation theorem, now we give this name, modulation theorem. It is originally modulation theorem is we multiply by a real signal, by a real sinusoidal signal. So cosine omega 0n. So this is just the same as what we had on the previous page. All we will do is we have those two parts. One is at omega 0, one is at negative omega 0 frequency, and then each part is a half. So putting together, I got the same energy as my time domain signal. How to prove that? Well, it's a cosine function, right? So it's cosine function. I can write this into this format: half of e to the power positive j omega 0n plus e to the power negative j omega 0n. So this is cosine function, cosine omega 0n. Therefore, you break that into two parts using the theorem of previous page, and easily we can prove that you got those two parts. Time shifting, you kind of shifted those two frequencies, at omega 0 and omega negative omega 0. So in this case, modulation, if you multiply a real sinusoidal function, what you did is you are bring this frequency domain signal into omega 0, or let me just call it omega c carrier, as we did before. Another one at negative omega c. So you bring that onto those two frequency. Now, but remember, because you break that into two parts, so each part has the energy is only half of the original one. Therefore, you adding together, you preserve the energy as you count it in the time domain. And then we have the Parsifal's theorem. Parsifal's theorem is a generalized form. We got the generalized form of Parsifal theorem of Z transform. So here I have two signal pairs, x1 and x2, with their Fourier transform, frequency domain signal here. So if I am going to sum over x1n times x2 conjugate, sum all these over, what we have here is I have the frequency domain signal x1 omega times x2 omega conjugate, then integration over one period, over 2 pi. Okay, divide by 2 pi. It's just, this is just a normalizing constant. Then those two parts will be the same. That's the Parsifal theorem. So the Parsifal theorem, if you remember before, we're talking about a special case when I am only dealing with one signal. Let's say x2n equals to x1n. We are only dealing with one signal. Therefore, the left of my equation becomes x1n times x1n conjugate. Now, what is this? This is x1n absolute value square, sum, n from negative infinity to infinity. And here is symmetry. That becomes integration negative pi to pi x1 omega absolute value square the omega, right? If I'm dealing with just one signal. So this is the energy of my signal. We know x1 and absolute value square, that's the instantaneous energy, or the instantaneous power, excuse me. So you sum over the entire thing over the time horizon, they get the energy of signal. Of course, the energy should be the same when you measure that in the frequency domain. So we have, this is the spectrum. You over one window and multiply that and divide by 2 pi, you got the energy measure in the frequency domain. So that should be the same. That's the Parsifal theorem. Okay. And then we have a windowing theorem. Windowing theorem is that I got those two signals, x1, x2, a product in the time domain, just a product in the time domain. So we mentioned before, we are doing a windowing. So filtering is we doing a element by element product multiplication in the frequency domain. Windowing is doing element by element multiplication in the time domain. Okay, then the frequency domain is written in this form. It's a summation of x1 lambda times x2 omega subtract lambda and integration d lambda, integration over one window of 2 pi. Okay. Now, what does this look like? This looks like a convolution. Okay, you can think that's a kind of a convolution in the frequency domain, right? We got a lambda on a constant subtract a lambda. So it's a format of convolution. Therefore, indeed, a multiplication in one domain becomes a convolution in the other domain. That's a window theorem. Now, windowing theorem, that's what, when we do is we have a signal in time. Let's say any signal. Then we multiply by a window function. This is time. But we are multiplied by a window function. So let's say this is a window, it's a rectangular. So what we do is we are doing a element-wise multiplication. Therefore, I am only going to take this, right? This, I'm only going to take signal kind of from here to here. Window. It's truncated by this rectangular box. So this is windowing. We take a window of that. Now, window may not be a rectangular box. It can be some smooth function. But we are doing a time domain multiplication. If I want to check with frequency domain, that's an integration. Okay. Lastly, we have here, if I have a differentiation in the frequency domain, that becomes in the time domain is my signal multiplied by this time variable n. So n times xn. Using the Fourier transform equation, we can prove that in the other domain, frequency domain, it's a differentiation. That's the capital X over the omega. Only that we got a constant. This is a especially imaginary symbol J here. So that can help us to simplify a lot of calculations, especially for the differential equation. You got a differentiation, and then you can always translate into the other domain, and it becomes a multiplication of the function variable, whether it's a time variable or other domain, that'll be a frequency variable.